Hello, this lecture is based on the Combinatorics in Graph Theory textbook, section 1.2, distance in graphs. First, we'll talk about some definitions and a few properties. So given a connected graph G, the distance from vertex U to vertex V is the length, which is the number of edges of a shortest path from U to V in G. And remember that a path is a walk with distinct vertices. We denote this distance by D, U, and V. So in this example, the distance between B and K is 4 because a shortest path from B to K has length 4. So here 1, 2, 3, 4 steps, and that is a shortest path. The distance between C and M would be 6. You can check that a shortest path would take 6 steps between C and M. Given a vertex, the eccentricity of this vertex is the greatest distance from V to any other vertex. In this example, if you look at A, the eccentricity of A is 5 because the furthest vertices from A, so those would be K, M, and N. The distance between A and those vertices is 5, and the other vertices are closer to A than those vertices. For this example, the vertices C, K, M, and N, those have the greatest eccentricity. So for each of these vertices, you can find a vertex with distance 6 from them. And the vertices in this graph with smallest eccentricity, which is 3, would be E, F, and G. So for example, if we look at F, no matter what vertices you choose, it's possible to get to F in 3 or fewer edges. And so some more vocabulary. So the radius of a graph is the value of the smallest eccentricity. So in our example, that would be 3. And the diameter of a graph is the value of greatest eccentricity. So in our example, that would be 6. So for exercises, I want you to find the radius and diameter for this graph, and also the radius and diameter for each of these special types of graphs. So the path graphs are denoted by Pn, and your answer would be different when the path graph has even or odd vertices, and the same with the cycle graphs. Your answer would be different depending on whether you have even or odd vertices. And do the same thing for the complete graphs and the complete bipartite graphs. And now we want to talk about the connection between graphs and matrices. So one reason why we might want to connect them is that when we have large graphs, their analysis often requires computer assistance, and computers are very good at working with matrix representations. And one possible way to represent a graph with a matrix is using the adjacency matrix. So given a graph with n vertices, the adjacency matrix is the n by n matrix whose ij entry will be denoted by this symbol, is defined to be 1 if I and j are adjacent. So if there is an edge ij in the graph, so here I is the row and j is the column, and the entry should be 0 if I and j are not adjacent in G. So in this example, I have a graph with 6 vertices, and this is the adjacency matrix. For example, if we look at row number 2 and column number 4, we see that the entry here is 0, and that is because there's no edge 2 and 4 in the graph. And this graph is symmetric in the sense that here you can swap the row and column, and the entry would be the same. And in this graph, there are 7 edges, and you can check that in the adjacency matrix, there are exactly 14 entries, which are equal to 1. So for simple graphs where there are no loops, the adjacency matrices have all zeros on the main diagonal. And depending on how you order your matrices, different orderings of the vertices may produce different matrices. Now, let's look at some nice properties of the adjacency matrix. So, because there is no edge between 1 and 6, the 1, 6 entry of the matrix should be 0. But now let's consider the 1, 6 entry of the matrix A times A. So to do matrix multiplication, what you do is, for example, we can compute the entry at row 1 and column 6 by taking row 1 of the matrix A, so the matrix on the left. In this example, we happen to have the same matrix. And then we take the column of the right matrix, and then we take their dot product. So basically we do 1 times, 0 times 0, and then 0 times 0, 0 times 1, 1 times 1, 1 times 1, and 0 times 0, and add up the sum. In this case we have 2, and that is where this entry comes from. And now let's think about what makes this dot product non-zero. So if we look at row number 1, we have this value 1 on the 4th position, and this represents the edge 1 to 4, and we are matching it up with the value 1 in the 4th position of column 6, which is over here. So this represents the edge 4 to 6. And another thing that happens is that you can look at the 5th position of the row and column. So here this represents the edge 1 and 5, and then we also have this value 1 here, which represents the edge between 6 and 5. So what happens here is that the entry in position 1, 6 of A squared is equal to the number of 2 edge walks from 1 to 6 in the graph. So the one such walk is the walk that goes 1, 4, 6, and the other walk is the one that goes 1, 5, 6. And you can check that there are exactly 2 walks from 1 to 6 that has length 2. So this one, so 1, 4, 6, and also 1, 5, 6. And of course there are many walks from 1 to 6, but these 2 are the only walks of length 2. Alright, so this is not a coincidence. So for any positive integer k, the ij entry of A multiplied k times is equal to the number of walks from I to j that use exactly k edges. So we prove this by induction. When k is equal to 1, this is true because of how the adjacency matrix is defined. The position at I and j is 1 exactly when there is an edge between I and j, so there is exactly a 1 edge walk between I and j. Now suppose that for every I and j, the ij entry of A multiplied k minus 1 times is the number of walks from I to j that use exactly k minus 1 edges. So this is the inductive hypothesis. Now, when you take a k edge walk from I to j, there must be an edge so that this walk can be thought of as a shorter walk, so a walk with k minus 1 edges from I to h, and then combine that walk with just an edge from h to j. So the total number of these kh walks is then the same as the number of k minus 1 edge walks from I to h, and you can just take this sum over all of the vertices h in the neighborhood of x. So here the symbol and x is the set of vertices in G adjacent to x. So this set is called the neighborhood of x. Now by induction hypothesis, I can rewrite this sum this way. I can just look at my adjacency matrix, multiply k minus 1 times, and look at the entries IH, where the sum again is taken over the same thing, the neighborhood of J. Okay, so now let's go to the next equality. So this next equality is true because for every entry hj in the adjacency matrix A, I'll have 1 if h is in the neighborhood of j, and I'll have 0 if h is not in the neighborhood of j. So I can safely just consider all of the vertices, not just the vertices in the neighborhood of j. And I can safely multiply with this term, because this term would be 0 if h is not in the neighborhood of j. So that is just equality. Now let me explain the last equality with the color blue. Okay, so this last equality is using the definition of matrix multiplication. So now I want to multiply A k minus 1 times the matrix A. So the rule for that is that the entry, for each entry ij, I take the row I of this left matrix. So I have position 1, 2, and so on until n. And then I take the column j of this right matrix. So again, I have a vector. And then I take the dot product of the two vectors. So I do position 1 here times position 1 here, and position 2 here times position 2 here, and do that for all of them and add up the sum. But that's the same thing as really doing this times this. And I do that for h from 1 to n. So this h is really like the position. Right, so that's why this last equality holds. So a corollary of this theorem is that if you know the distance between I and j, so that is the number of edges of the shortest path from I to j, then you know that how to compute the powers of the adjacency matrix. So the entry would be 0 for the k power of A if k is less than this distance between I and j. Because there's no, because the shortest path from I to j is still, the length of the shortest path is still longer than k. Okay, and now another way to represent a graph as a matrix is to compute what's called the distance matrix. So instead of the adjacency matrix, we can record for every entry ij in the matrix the distance between I and j. So for these exercises, I want you to compute the adjacency matrix and also the distance matrix for each of these special types of graphs. So for the path graph, label the vertices from one end of the path to the other, like this would be your P4 and this would be your P5. So your answer will be different depending on whether the number of vertices is even or odd. And for the cycle graphs as well, your answer will be different depending on whether you have odd or even vertices. So k, m, n is a symbol for a complete bipartite. So this is the graph for the complete bipartite graph 2, 3. And kn is the complete graph. For the second exercise, I want you to use the theorem that we just proved to compute a to the power of 3, where a is the adjacency matrix of the complete graph on 4 vertices. So for example, using the theorem, I know that the entry 1, 1 would be the number of walks from 1 to 1 of length 3. So let's compute that. So starting at 1, I have 3 choices. I can go to 2, 3, or 4. So that's why I have this number 3. And then from there, I really want to make a triangle. So if I had gone to 2, now I have 2 choices. I can go to 3 or 4 before going back to 1. And that's why I have 2. So the entry 1, 1 in this matrix is 6. So I want you to do that for all of the other entries using theorem 1.7. And then in the last exercise, so prove that for A times A, the diagonal entry j comma j is really the same as the degree of the vertex j.